Good evening, everybody. Welcome to the Alumni Lecture Series. My name is Ken Meisner. I'm the Executive Dean for the Faculty of Science and Engineering. And I see we've got a great crowd this evening. We're already up at 120, 121. Hopefully it's a good evening, or maybe morning or afternoon, depending on where you're at. Hopefully everybody has got their biscuit or cookie and a cup of tea or coffee to enjoy the lecture series, and really appreciate everybody coming this evening and spending the time with us. This lecture series is allowing some of our alumni, our distinguished alumni, to present their research and their interests. And we'll talk to you a little more at the end about some upcoming opportunities. But tonight we're going to have Dr. Ben Evans. And just a little bit of housekeeping before we go. This is kind of like the health and safety portion of a virtual interview or a virtual lecture. We'll have a question and answer session afterwards. If you could enter your questions in the Q&A button down at the bottom, we'll be able to moderate those and get Dr. Evans to talk about some of those. So in terms of a brief introduction, Dr. Evans is a Swansea boy, so he grew up in Swansea before leaving to study aeronautical engineering at Cambridge. The pull of Swansea was too great and brought him back for his PhD, where he focused on computational fluid dynamics, particularly looking at hypersonic applications, which leads very well into tonight's lecture series, certainly. In fact, he won the 2008 Mike Criswell Prize for computational mechanics. So a distinguished career as a PhD student, certainly. Today, he's an associate professor here in Swansea University in aerospace engineering, sorry. And he sits on the design team for the Bloodhound Land Speed Record project with responsibilities in aerodynamic vehicle performance and modeling. So he'll certainly be talking to us from a great experience on this. And I think we're all really looking forward to hearing it from you. So Ben, if I could, if you want to hop on, looking forward to I love the title, The Design, Build, and Testing of the World's Fastest Car. Bloodhound LSR, an engineering adventure. And any of us who have been in engineering know it's always an adventure. So thanks, Ben, and looking forward to it.
Thank you very much, Professor Meisner. Can I just check, can you see my screen at this point?
Yes.
Can you see my slide? Fantastic. Well, diolch yn fawr yr athro Meisner. Mae'n pleasure I fod gyda chi heno. It's a pleasure to be with you all, wherever you are around the world this evening. And this is an alumni lecture series, which has caused me to reflect back on my time as a student at Swansea University. I'm now, of course, a member of staff here. And it's prompted me to take this opportunity to thank two people who really are the people, the reason we're here this evening, and certainly the reason I'm back here in Swansea. Professor Ken Morgan and Professor Ubay Hassan. They were the two people who inspired me and convinced me that the right course of action in my career was to return to Swansea, having grown up here, and embark on a PhD in a field called computational fluid dynamics, which is something that I will be touching upon this evening. So hopefully we're flicking through my slides now, and this is all working. So there are four parts to what I want to chat to you about this evening. Part one, we're going to look at some of the tools that we've developed here in Swansea and how we've applied those to the design of this incredibly fast car, this land speed record car called Bloodhound. I'll briefly talk about how we went about building the car, what it's made of, what that looked like. And the focus really of the talk this evening, which I haven't had the opportunity to talk that much about, even though it kind of goes back to a lot of work we did in 2019 because of what's been going on in the world in the last year. So you are some of the first people to really explore some of the data that we're going to look at in terms of testing of Bloodhound. And a lot of that work was done in 2019. And then quite timely this evening, really, because I'm sure lots of you who've been following the project in the news will have seen that it's back in the headlines this week. So I'll try and answer that perennial question on this project, which is what on earth happens next? So just in case there are any of you out there who aren't sure what the Bloodhound project is all about, or need a little recap. I'm going to play you a short movie. I'm going to cross my fingers that all of the streaming and audio works on this. And hopefully this will give you a feeling for what this project is all about from a technical engineering perspective. So I hope that has whetted your appetite for what is to come. So part one of this talk is all about aerodynamic design. When we were approached here at Swansea University back in 2007, I was just coming out of my PhD years, and we were asked to take the lead on the aerodynamic design for this new initiative of Richard Noble, a very brave, adventurous chap who held the land speed record back in the 1980s, was the director of the thrust supersonic car that still holds the land speed record today. And we bravely or foolishly, depending on which way you look at it, took him up on that challenge. And we said, okay, we've got the technology here to do this. We'll help you out. But it quickly became apparent to us that this was a massive undertaking. The ambition back in 2007 was to design the fastest car in the world, a land speed record vehicle capable of 1,000 miles per hour across the surface of the Earth. To put that into perspective, at that time and still to this day, the fastest car that had traveled across Earth as a land speed record car was Thrust SSC, reaching speeds of 763 miles per hour, just above the speed of sound. Here are some of my my favorite land speed record cars going back through the history of the land speed record. Two of them, Babs and Bluebird. Part of the reason they're my favorites is because they broke the land speed record right here in South Wales, just a little bit along the coast at Pendine Sands. But when we started looking at this and how much of a challenge this is going to be, we quickly realized to push deep into that supersonic speed regime where you're traveling significantly faster than even sound itself travels was going to be a task. At these kind of speeds, vehicles, which of course are usually aeroplanes, generate shock waves. Those shock waves are very sudden, almost instantaneous changes in the pressure field, the distribution of pressure around the vehicle. And of course, aircraft have the luxury that they're out in the atmosphere. They've got a lot of space around them. These shock waves can fan out around the aircraft. But by definition, a land speed record vehicle is a car on the ground. And it quickly became apparent to us that trying to get our heads around how these shock waves would interact with the ground plane across which the car was rolling, whether those shock waves would reflect off the ground, damage the ground, affect the wheels, and the way the wheels interacted with the ground was going to be a big part of understanding whether or not this was even possible. Now, in the past, I mean, certainly going back 20 or 30 years, automotive aerodynamic design or aerodynamic analysis would have been done using a real physical wind tunnel. Now, we chose early on not to go down this road with Bloodhound for a whole bunch of reasons. One of which is they're very, very expensive. We do have an impressive suite of wind tunnels here at Swansea University, but none, unfortunately, where you could, first of all, get the flow speed up to supersonic speeds, but more importantly, or a bigger challenge again, is actually rolling the ground plane underneath the model at supersonic speeds. they're not only extraordinarily expensive to use as a design tool, they're very slow to use because, of course, every time you want to test something new, you physically got to change the model, manufacture a new model, or tweak the model in the real world. So we decided all the way back in 2007 that the way we were going to design this car from an aerodynamic design perspective was using computer simulation. We are extremely fortunate here in Swansea to have world-leading computer simulation technologies at our disposal. And a lot of the reason for that is because of this chap here, Professor Oleg Zienkiewicz, who arguably is one of the pioneers or the grandfather of a method that underpins a lot of computer simulation today across a whole range of disciplines called the finite element method. I'm just thinking back to my student days when I was a PhD student here in Swansea. I was lucky enough to spend quite a bit of time with Oleg in the last few years of his life. Every Friday afternoon, in fact, I would go and see Oleg at his home in Mumbles, which is a little village just outside of the city of Swansea where he lived. Because although his health was deteriorating towards the end of his life, and certainly his eyesight was deteriorating, he was as bright as a button and was still getting lots of correspondence from academics around the world asking him for his advice on things. And I used to sit with him in his study and read letters to him, and he would dictate responses for me to respond. So I got to know Oleg very well. And he pioneered a lot of the tools that we've used on Bloodhound. Now, essentially, computational or computer simulation boils down to a number of steps. Whatever method you're using, it basically boils down to, do we understand this problem well enough? Do we understand the physics of the problem well enough to describe the problem mathematically? Can we write down a set of equations or an equation that describes the phenomenon? That's the first challenge. If you can do that, we then ask ourselves the question, well, can we solve this equation? Now, very often in the real physical world, those equations are complex, they're coupled, they're often differential equations or partial differential equations. And we come to the conclusion that actually it's very, very difficult, if not impossible, to solve them exactly. So we decide, well, instead, let's solve them approximately. We come up with approximate solutions to those equations. We then realize that in order to even get approximate solutions to those equations, we're going to need some very powerful computers. And that's where computers step in and help us out. And then the final part of the process is to look at all the data that these computer simulations provide us with and do something with that, visualize it or process it. Now, in the context of aerodynamics and aerodynamic modeling, we call this field computational fluid dynamics, or more easily the acronym CFD. So when you hear me this evening talking about CFD, this is exactly what we're talking about. It's virtual wind tunnel testing, essentially. Now, as I mentioned at the start, I'm not going to go into too much detail this evening on the actual CFD method that we've used, because over the years, I've given many, many lectures going into the details of this. If you are particularly interested in that, there's a reference there of a paper that we published almost a decade ago, looking into the specific methods that we've used. But it is worth mentioning this evening that we had a lot of support over the years from a whole range of people providing us with computer resource, one of which is the Supercomputing Wales organisation, who provided us with one of the largest supercomputers in the country to run our simulations on. Now, at the end of the CFD process, the thing that we actually study as designers, aerodynamic designers, to help us evolve the design of a vehicle, and in this case, of course, Bloodhound, often looks something like this. So what we've done with the data that comes out of the computer simulation here is process it so that we can see the pressure field over, in the first instance on the far left there, the underside of the car, and on the second image, the right-hand part of that left figure, the actual surface that the car is rolling across. Now in this image, and what we are seeing animated on the left there is one of the very early configurations of Bloodhound, before we'd solved a lot of the aerodynamic headaches that we hit up against. And you can see, particularly at the back of the car, the underside at the back, that there are some big changes in the pressure that the underside of the car is experiencing. And those pressures translate into forces. So we were also predicting huge force changes as the car accelerated from low subsonic through to supersonic speeds. So we use this sort of analysis to help us evolve the design of the car I'm hoping we're going to see this. Yeah. So on the right-hand side, there are some subtle but significant changes, particularly at the back of the car, which is at the bottom of the vehicle in this image. And one of the things hopefully you can spot is that the size of those pressure variations as the car is accelerating, as the Mach number is changing, are massively reduced on the right-hand side. And that was one of the big headaches that we had to overcome during the design process. So to cut a very long story short, we went round this design loop many, many, many times. Between 2007 and 2015, over that period of 7 or 8 years, we went round this loop. I mean, what's displayed here looks like 12 times, but in reality, it was a lot more than that. And every time we changed something to do with the external geometry of the car, it would come to me, we'd run our suite of CFD simulations, try and understand what was happening in terms of the aerodynamics, and then I would provide my guidance to the other engineers on the design team on where we should go next. And eventually we ended up with that final configuration that's labeled there config 12, which was the car that we actually built. And this is the point in the process where I got to kind of sit back and relax. So we're talking about 2015, 2016, that sort of time now, where we here at Swansea basically provided the outer mold shape that this car needed to be to keep the drag as low as it needed to be, and also a shape where we could control the lift acting on the car and the lift distribution across the car, all the way from low speed up to Mach 1.3. And we handed that design over to a whole team of engineers, far cleverer than I in terms of how you actually then design and build the underlying structure of the vehicle. And it took us 2 years to get the car built. It took us that long for the same reason that lots of things have taken a long time on Bloodhound, because we were completely reliant on external sponsors, providing us with parts, providing us with materials. And actually, what was available to us for free dictated some of our design decisions. The wheels on the car, for example, in the earliest configurations of Bloodhound were pure titanium wheels. Of course, when we needed to get the car built then, we started asking companies around the United Kingdom if they were willing to donate to us 4 large blocks of titanium for free. We didn't get very far, so we ended up having to redesign and look at an aluminium alloy design. So in terms of what we've ended up with in terms of the underlying structure and build of the car is basically a car of 2 parts. The rear half of the car, as you can see here, is a metallic space frame type structure, very similar to the type of structure you would see beneath the skin of an aircraft, an aerospace vehicle. And it's that frame, that metallic frame, that's translating the stresses and the loads through the car. The front half of the car, however, is a carbon fiber monocoque, very similar to the kind of the way that a Formula One car today is designed. So the actual carbon fiber skin itself is transferring loads through the vehicle. The reason we made that decision was that the back half of the car are lots of the components that we knew we regularly need access to. So things like the jet engine, the rocket systems, hydraulic systems, fuel pumps, and so on. And the carbon fiber solution at the front is brilliant until you decide that you need to start punching lots of holes in it to get access to things inside. The front of the car has got, obviously, Andy, our driver, so he does need to get access to the cockpit, but also fuel tanks, electrical systems, steering systems, which were bits that we wouldn't need to be so regularly accessing, which is why we went for this kind of half cutting edge motorsport design, half cutting edge aerospace design. Here are a few images from over that period, 2015 to 2017, of the car in various states throughout the build. And top left there is a younger looking me, which is a bit depressing, isn't it? With a bit more hair and also a bit thinner from 5 years ago, because I was the first person, this is one of my claims to fame, the first person to actually sit in the cockpit of Bloodhound. When that monocoque shell arrived at our assembly site at the centre of Bristol, and we pulled the wrapping off it before anybody could tell me I wasn't allowed to. I jumped in and asked to have my photo taken just so I could say I was the first person to sit in Bloodhound. So we got the car built eventually. And then, of course, it was time to see if Bloodhound could do what we, in terms of the aerodynamics, had been promising it would be able to do. The first thing we did was take the car down to Newquay in Cornwall, just to run some shakedown tests to make sure that the steering system worked. A couple of other things that we were particularly interested in during the low speed testing, and I'll show you, I'll play these movies just to give you a little feel for what that was like. So this is Andy driving on the runway down at Newquay Cornwall Airport, which is one of the longest runways in the UK, but we were actually able to secure quite a bit of time on the runway. And we wanted to know a couple of things. So one of the things we wanted to know was, could we get full afterburn or full reheat thrust from our EJ200 jet engine from a standing start? And as you'll see on the right-hand side in just a moment, the nozzle is contracting, the car starts rolling almost immediately. Now, the reheat kicks in on the jet engine, giving us full thrust almost from a standing start, which we didn't think we were going to be able to. We would have to gently bring the engine in, not to choke the intake. But that was brilliant news from an aerodynamics and performance point of view. We also wanted to figure out how well the wheel brakes. We've got fairly conventional brakes on the wheels, front wheels of the car, and the wheels of the car, to bring it to a stop at low speed, thrust low speed, 200 miles. We just wanted to make sure, of course, that they worked on the runway, and they worked brilliantly. So from an engineering point of view, and also from a spectacle point of view, the trials in Newquay were a phenomenal success. We attracted tens of thousands of people down to watch this. And for me, this was the first time that, if I can pause that video. For me, this was the first time I'd seen this car in reality. I remember the day that I stood alongside the runway, and after a decade of working on Bloodhound, where it had been basically images on my computer screen. You know, Bloodhound had never been much bigger than, you know, my computer screen was. And all of a sudden, here's the real thing, 13 meters long, creating an awful lot of noise. It all suddenly became real. But one of the things we discovered at Newquay, and this was something that I was completely wrong about in the run-up to our low-speed testing. I'd been saying to the team in the couple of years leading up to this, where getting in sponsors was a real challenge. It's always been a real challenge on Bloodhound. That as soon as we get this car built, even if it's the bare bones of Bloodhound, and we run it down a UK runway with a big flame out of the back of it, all our issues about trying to get sponsors on board will go away. There will be companies queuing up to put their name on the side of this car. And in fact, the opposite happened. And I think the main reason for that is, of course, it all became very, very real. And the risks involved and the danger involved in putting a human being in a car like this, and then us saying, well, you've seen it at 200 miles an hour, we're going to take it 5 times faster, in fact, scared sponsors away. So as many people will know, a year later, in fact, the project did run out of money completely. It went into administration. We thought it was the end, until a very brave chap called Ian Warhurst, who we'll see a little bit later on, stepped in and he said, this is crazy. You've got a car here that has the potential to be the fastest car in the world, and the administrators were on the verge of cutting it up for scrap and cutting it up to extract some of the high value components on it, like the jet engine. So we went from the project is over to there's money in the project. We're going to South Africa to see what it can do and to start the high-speed testing program in the space of a few days. So over those few months from the end of 2018 and early 2019, we started preparing the car for its trip to the Hakskeen Pan in South Africa. Now, this is an incredible place. We'd been preparing this site for a number of years in the lead up to the high-speed test program. It's brilliant for land speed record testing for a number of reasons. It's large. It's the pan itself is 12 miles long with overrun at either end of the track. it's incredibly flat. I'm not sure how well you can see from the graph there, but the elevation change of the pan over scales of a couple of kilometers is of the order centimeters. And it's a lovely, it's a solid surface, but it's soft enough to allow our solid metal wheels to kind of bite into the surface to get some grip. So we took the car to South Africa to see what it could do. And when we started getting data back from the car, I was quickly very relieved. So what I'm going to show you now is a short video, and it's me talking to you again, I'm afraid. But this is me talking to you from South Africa during the testing program back in 2019. So my name is Dr. Ben Evans. I'm an associate professor in aerospace engineering at Swansea University. The exciting point we've arrived at now with Bloodhound, as one of the people involved in the aerodynamic design of this car, is we are taking Bloodhound into the real world. It's been a theoretical model on a computer screen for a decade where we've been predicting, using aerodynamic computer modeling, we've been predicting the pressure distribution over the surface of the car. What we've got now really is the world's fastest aerodynamics laboratory. This is, as far as I'm concerned, a piece of scientific equipment where over the surface of the car we've got almost 200 pressure tappings at critical points on the car where we want to be measuring the pressures on the surface of the real car and comparing that with the computer model that we used to design it in the first place. Of course, what I'm hoping and what we're seeing so far is that the mapping between the real world measurements at these pressure points and the computer model that we used to design the car in the first place are mapping very well together. That's up to Mach 0.6 as far as we've pushed the car so far. And of course, what I'm hoping is that we continue to see that close mapping as we accelerate the vehicle in future tests.
So what I'm looking at here is a comparison of the actual data we pull off of the car compared to the CFD simulations that we've done in the years leading up to the project coming out to the pan. This is really a big moment in terms of making sure that the models that we've based the entire design of the car off and the entire performance of the car that we can expect to the actual data that we are seeing here on the pan. So far they're matching up really well, which is very reassuring. So as you can see from this plot, you can see the colour mapping over the entire car. That's the CFD predicted model. Because it's a nice computer simulation, we can see everywhere all over the car. On the actual car, we can only see at particular points that we've put holes into the car and we can measure the pressure at those points. So what you're seeing here is all of these points across the car, and if they're green, they're within our tolerance band, and if they're red, they're outside. So what you can see here is a nice green Christmas tree effect, which means everything's looking good.
So I can't begin to explain to you the relief I felt when we started pushing the car up to kind of significant speeds where the pressure distribution that we've been predicting over the surface of the vehicle was becoming interesting. And we were seeing plots like the one on the right-hand side there, where at the various pressure sensor locations across the surface of the car, and there were 156, I think, from memory, of these sensors over the car, the vast majority of them were within 10% in terms of the absolute pressure being measured to the prediction that the CFD model that we'd used to design the car had been predicting. It wasn't perfect, nothing ever is. And what we spent quite a bit of time doing while we were out there, and you met Jack there, who's one of my research team, he has the job title Data Boffin, was we would look at plots like this, where we would take the data from all of those 156 sensors at different speeds that the car was traveling at, under different configurations during acceleration, during deceleration, and look at, well, what were the pressures that we were measuring at different points on the car against what we had been predicting from the CFD model. And of course, if you had a perfect alignment between those two data sets, all of these points that you're seeing on these graphs would sit on that nice y = x line. They don't, it's not perfect, but the correlation was significant enough to give us the confidence that the CFD model, in fact, was doing a very good job of predicting what was happening to the car. We're engineers, we want to understand everything. So of course we did look at, some of our worst case sensor locations. So a lot of the time I spent going, okay, so here's a position on the car where what we're measuring from the sensor isn't aligning very well with the CFD model. And very often you would go and look at the car, find that sensor port and discover things like, well, it's completely clogged with dust. or there are particles blocking the tubing. So it's actually an experimental error that's causing that misalignment between the measurement and the CFD model. And this is work that's ongoing. We're still trying to fully understand all of the data that we got from Bloodhound. It's reassuring, I'm sure for you, that the vast majority of the sensor locations over the car, when we plotted, and I guess the important graphs to have a look at here are the ones where you've got the red and the blue curves, the left-hand side graphs. Here, the red curve is what the CFD model was predicting in terms of pressure as a function of Mach number on the x-axis, and the red curves are what we actually measured at some of the sensors where that mapping was very, very good indeed. One of the other things that we were measuring on Bloodhound during the high-speed test program were the loads on the wheels themselves. So we had load monitors that we could infer from suspension deflections on each of the 4 wheels of Bloodhound, because, from a safety point of view, you can naively perhaps say, well, it's as long as you keep all 4 wheels on the ground, and you can ensure you're doing that by making sure there's positive load acting on all 4 wheels. There's nothing to crash into because we've got this great big open pan. As long as the 4 wheels are always touching the ground, what can possibly go wrong? Obviously, it is a little bit more complicated than that, but that was one of the things that we were measuring at all times. And I remember this eureka moment when we got up to run 33. Remember, we've been slowly stepping the speed of the car up in small increments. This was a run where we got up to 562 miles an hour, which is just above Mach 0.6. And the black line you see in this graph here is the total load on all 4 wheels added together. And then what was interesting was then to go, well, how is that distributed between the front axle, which is the blue curve, and the rear axle, which is the red curve. And this pink line here is the speed that the car was traveling at. So you see it hits peak speed at about 60 seconds or so. And there's some obvious things that you spot here. So at the start of the run, when the jet engine fires up, there's a transfer of load from the rear wheels onto the front wheels, exactly as you might expect. And we started in these higher speed runs at the back of the car, seeing this slight camel hump phenomenon at around about peak speed. And initially that puzzled us until we realized that actually what was happening here is that we were reaching the point aerodynamically of maximum downforce, and in fact passing through it. The curve on the right-hand side here is from our computer model. So this is what the computer model was predicting the total downforce, particularly at the rear of the car, would be doing as a function of Mach number. And you see as the car accelerates initially from Mach 0.3 to around about Mach 0.6, it reaches a point of maximum downforce, and then you start losing your downforce, and eventually the car will be generating some lift. And actually, we were just hitting the point exactly where the computer model had predicted we would hit peak downforce, and we were now going through that point and losing our downforce. And in fact, as the car pushed faster, this is the final 628 mile per hour run that we did, that camel hump phenomenon that you see here in the red curve is even more pronounced. You see that we hit this maximum downforce point, we accelerate through that maximum downforce and lose some downforce, and then we regain it as we decelerate down. So seeing that kind of correlation between our predictions over a period of 10 years come into reality on the desert was incredibly reassuring. What we were also able to do by the end of the high-speed test program is take all of the data from our CFD models, particularly in terms of the drag prediction that the CFD model was coming up with, and feed it into an overall kind of dynamic performance model for the car. For those of you who are a bit geeky like me, we basically did this in MATLAB, and it was the way we did it was just to integrate Newton's second law, force is equal to mass times acceleration. So we'd feed all of our predicted forces in. Some of them were predictions on jet thrust, some of them are predictions on aerodynamic drag and rolling resistance. And by the end of the process, our model was able to incredibly accurately predict the performance of the car. So don't worry too much about the dotted lines here, which are related to jet thrust. But what's important here is that we were able to do this modeling so that before a run, if we wanted to hit, for example, 628 miles an hour, we could predict for how long the jet engine would need to run for, to get that speed, and importantly, where on the track we would hit that speed, and then how long it would take to decelerate back down to zero. So that was an important development that we achieved during the high-speed test program. So just to give you a feel now, before I kind of wrap up and give you a little hint at what the future might look like for the project, let me show you this, this final little video that will give you a feel for what we managed to achieve while we were in South Africa in 2019.
And convoy control, approved transit track gate northern corridor start point and report in position.
Driver is now in Bloodhound. Over.
Convoy control, good morning. Temperature is +25 and pressure 921 millivolts.
Check that. Control engine confirm, all is bloody good, and we're just celebrating for a few minutes. Over.
6:28. Look at that. Smashed it. It's a bit of a surprise. 9 minutes. What's the potential, mate? Doesn't matter. Pictures, man. Well done, buddy. 6:28. Thank you, Carver.
Yeah, absolutely delighted. Our first 600-mile-an-hour run. Personally, I'm just a tiny bit miffed. My job is to control the car as precisely as possible, so I was trying to target about 605 just to make sure we got the 6 number. We actually finished up with 628 miles an hour. That is actually outside my control. When I lifted off the throttle, the way the jet engine winds down changes with speed, and it gave us more power for about another half second, and that put the extra speed on, finished up another kilometre further down the track.
Stop that video there just to make sure that I leave enough time for some questions at the end. So it was a phenomenal success. We came back with everything we wanted. And then at the point where we were saying, we've de-risked the project, we know this is going to work. Who wants to come on board as a sponsor? We've got a blank side to the car. COVID hit. So you may well have seen in the news this week that the project is now up for sale. So within the next 12 months, we are going to discover whether or not someone steps up to take this on, and we take the car back to South Africa to attempt a land speed record. And the first target we would go for is 850 miles an hour. Or there is a spot for the car in the Coventry Transport Museum, which is where Thrust SSE lives. I hope it's the former of those two, of course, but just like everything to do with Bloodhound, we just don't know where we're going next. That question that I keep getting asked of, is a 1,000 mile per hour run possible? Based on what we learned during the high-speed test program, the answer is yes, just about. It would be very, very tight if we ever did get to the point where we could attempt a 1,000 mile per hour run. The car is capable of it. The big question is, do we have enough track at Hackskeen Pan to achieve it? So where do we go from here? I mean, in terms of my work, what is as exciting as, you know, what's been happening with Bloodhound is now that we're working really hard to spin out some of the ideas and methods and technologies that we developed specifically for Bloodhound into other more conventional applications. I say conventional, applications like the reaction engine Skylon spaceplane. That's a project that I'm currently working on. We've also developed a partnership recently with a company called Faraday to develop a bioelectric commuter aircraft. And we're also applying some of these techniques to the design of high-speed hulls on motorboats. So there's lots of exciting research that has been inspired by Bloodhound, whatever happens with the Bloodhound project from here, which is great to see. So I'm going to stop talking there and just say diolch am wrando. Thank you very much for listening. Off the back of this seminar, of course, if you do have questions, feel free to get in touch with me on Twitter or via email. And if you want to find out any more about the research I do, the QR code for you to scan is there also. So I will stop speaking for a moment and invite Professor Meisner back to chair the Q&A.
Thank you very much, Ben. I think at this point we would be giving you a big round of applause. So if everybody could go ahead and give Ben a...
I'll imagine it.
There you go. It's a very COVID kind of round of applause. So thanks a lot. What a amazing project and amazing work you've done on that. So glad you came back to Swansea to
yeah, me too.
You know, and I would say, you know, for me personally, it's great to see the engineering design process in action with what you've shown today and the way that went over such a long period, including, you know, some of the parameters like materials availability. So that was just fantastic. So we will get to the Q&A now. So Ben, I'll just start working my way down the list here. The first question's from Mason. Why hasn't the Bloodhound achieved the land speed record yet?
Good question. A question I keep asking myself, trust me. I mean, ultimately, we have had everything thrown against us. I mean, to go back to the start, we launched the project in 2007 with the objective of wrapping it up within 4 years. That was my goal, okay? I was planning to be on this project and out of it and on to other things by 2011. Of course, the global recession hit in 2008, which meant that we had a real struggle in getting sponsors on board. And it's just been a slow slog in terms of bringing funding in. I mean, the reality is there were engineering challenges that took us longer than we'd anticipated in terms of the aerodynamic design. But really the thing that slowed us down is just bringing funding in. It's, you know, nobody's ever going to get rich off a land speed record project. So it's very difficult to convince investors to get involved. You've got to really love it to want to do it. I'm still hopeful we will get there. How long it will take us to get there, I don't know. But we're going to do our very best.
Excellent. Thanks. We've got a little less technical one here, a more human question. And that, what did it feel like thinking that 10 years of work was going down the tubes and then a few days later, it was okay?
Yeah, it has been an emotional roller coaster, I must confess. I mean, I'm very lucky, to be fair, that my day job is that I teach. I'm a lecturer at the university, right? So unlike some of the engineers on Bloodhound who literally lived and breathed this was their full-time job. I've always had a whole bunch of other fascinating, interesting stuff to fall back on when Bloodhound goes quiet. So, you know, the job I love is here at the university teaching and doing research, and Bloodhound is this kind of cherry on the top that I get to do every now and again when things are going well. So, but yeah, you know, back in tail end of 2018, where we went within the space of a few days from being told the administrators are wrapping this up, they're going to cut the car up, the jet engine's going back to Rolls-Royce, it's over. And if they'd done that, it really would be over. To there's this chap called Ian, and he's going to fund us to get to South Africa in the space of a couple of days was quite the emotional roller coaster.
I can imagine the depths to the heights.
Yeah.
So just following along that same theme, question from Ellie here was, what was your favorite part of the project?
Yeah, that's a really good question. I would say, I mean, bizarrely, perhaps, probably not necessarily the going to see it in South Africa. I mean, that was incredible. It was a spectacle. It was kind of, in some ways that, one of the highlights of the project. But I think for me, building up these amazing relationships with some brilliant engineers from companies, all across the world who have partnered with us on this. I think for me, like, I've never been a petrol head or a speed freak. I wasn't interested in the land speed record before I got involved in this. What has really kept me engaged is two things: that kind of the academic challenge, I guess, of like, how do you do this? Is this a solvable problem? And working alongside some brilliant people in trying to solve the problem, who are now friends for life, and also seeing the impact the project has in the wider sense of inspiring people. The number of people who are have joined the Bloodhound fan club or have got involved in the Bloodhound education program. And particularly, we've got a lot of students here at Swansea now who come to me and say, the reason I chose to study aerospace engineering is because somebody came into our school to talk about Bloodhound and I got interested in aerodynamics. So seeing that come to fruition for me really is what this is all about.
Excellent. Thank you. I got a technical question here, and that was, what software was used for the CFD analysis?
Yeah, good question. So we used all of our in-house software. It's a system called Flight 3D. In the presentation, I did share a little reference to kind of some of the more geeky research publications on it. It's written in Fortran. We run it on a large PC cluster high-performance computing system. So it's a fully parallel code. The parallelization is implemented using MPI. I probably don't want to go into any more technical detail than that, otherwise people will start tuning out. But get in touch with me after the session, and I'm happy to follow up with you on that.
No, anything that's done in Fortran is great stuff. Absolutely.
Old school.
Exactly. There are a couple questions on here about buying it. Is there interest? I don't know. Maybe we could start a GoFundMe thing. What sort of price are we looking at?
Yeah. So I don't know is the honest answer to if you wanted to come in now and buy the project, which is the situation we're in. We've spent a year trying to convince sponsors to come on board and have run the end of the course for that. So now Ian, who owns the project at the moment, Ian Warhurst, the entire project is up for sale. How much it's up for sale for, I don't know. I think you probably have to inquire about that. To give you an idea, we think to get the project over the next milestone, which would be an 850 mile per hour land speed record attempt, we think we're talking about somewhere in the region of £6 to £8 million to achieve that, which I know, to you or I, that is obviously an awful lot of money. But, there are companies and people out there who have that sort of money. So, I'm an optimistic kind of guy. So there's a part of me that just thinks there's no way this thing is going to end up in a museum before somebody steps in and says, no, let's do this. Let's make it happen.
Yeah, somebody's got to try it. Absolutely. I think this kind of goes on to it, tacks onto that question. And that was, why didn't you go for the land speed record? And I'm sure that has to do with what you were just mentioning with the extra necessary investment.
So in terms of when we went to South Africa?
Yeah, when you went to South Africa. Yeah. Yeah.
So we never intended to try and break the record on that first attempt for a whole bunch of reasons. First of all, it only had the jet engine fitted. So we didn't have the rocket system on the car when we went out in 2019. We think, looking at the performance models, we're on the cusp of being able to break the current record with just the jet engine. The issue you have, the things that ultimately dictate your top speed are two. One is what's your thrust to drag ratio. The second is how long is the track you've got. Yeah. So if we had an infinitely long track and we could take a long time to get to top speed, we could probably break the record with just the jet engine, but we've got to get up to top speed and get back down in 12 miles, which means you need a big thrust to drag ratio. what was the other? So we never intended to try and break the record when we're out in South Africa. It was really all about validating the design, de-risking the project. So we wanted to get as much data as we possibly could up to speeds that we felt were going to be safe. So we took the car to Mach 0.82, so 82% of the speed of sound, which is pretty fast for a car, trust me. And we now have masses of data that help us convince, well, ourselves, first of all, but also the wider world and potential investors that this car can do it. This, the CFD model we used to design it was right. So that's the reason we didn't go for it in 2019.
Very good, thanks. And here you talk about the design a little bit here. There's a question, how did you know where to begin with the design?
Yeah, good question. Well, I mean, the core team that I joined in 2007, I mean, when I joined the team, there were, I think the design team had 3 people in it, and it expanded to about 40 or so at the peak of the project. And that core team were the people who were involved in the Thrust SSE program, so the current land speed record car, which incidentally Swansea also did the aerodynamic modeling for. So we learned, I say they learned a lot, because I was a school child when Thrust SSE broke the record. They learned a lot about what to do and what not to do from the Thrust program. And I think one of the lessons they learned to try and minimize the pitch sensitivity of the car, which is obviously critical to avoid that disaster scenario of a backflip. We wanted to make the vehicle as long and slender as possible. That was always going to minimize the pitch sensitivity. So we kind of started off with these kind of basic principles of let's try and minimize the pitch sensitivity by making it as slender as possible. Also, we know theoretically there are shapes such as the Sears Hark shape, which minimize supersonic drag. So you start with something like that, and then you introduce all the pragmatic constraints, like the driver's got to see where he's going, so you need a windscreen. The jet engine needs air, so you've got to stick an intake on it. It's a car, so it's got to have 4 wheels. So you start introducing some of these pragmatic factors, and of course, it then starts evolving into the shape you see.
Excellent, great description, and great plug for Swansea on the SSC, the Thrust SSC as well.
I'm doing my best.
Penelope has a really interesting question, particularly given the new interest in hypersonic transport. Yeah. And what advice would you give to a 14-year-old who would like to study transport design?
Oh, do it is what I would say. We need more engineers and scientists in this world. Okay, there are massive, we're all aware of the fact that there are massive global challenges coming our way. The reality is, when this current predicament that we're in, COVID-related, passes, and it will pass. It's hard to believe it sometimes, but it will pass. We will travel again. And the reality is people will want to travel further, and they will probably want to do that faster. Whether that's right or not, that's a different question. I think the job of engineers is to say, well, if we are going to end up doing that, how are we going to do it as effectively, as efficiently, as sustainably as we possibly can? And, on the surface of it, I guess one of the criticisms of Bloodhound, and I understand this, is that it doesn't appear to be a particularly green project. But actually, the big goal of Bloodhound is not for us all to be driving around in jet-powered cars in the future. It's to inspire a whole bunch of engineers who will, in the future, design the technologies of the future where we can do these things completely sustainability. My dream, to put it out there, and I've never said this to anyone, right, is that we get Bloodhound across the line, and then we go, can we use Bloodhound as the footprint for a carbon neutral land speed record car that could do the same thing with no CO2 output, which I think is just about technically doable. That would be my, if I could plan my career path to retirement, it would involve doing that.
Excellent. Well, that would be wonderful. And it's a great dream. It really is. We do have a question from Kate here on how much has it cost so far?
Yeah, it's a good question. I don't know the exact figures. We're into the ballpark. We're into the kind of 25 million plus ballpark figure. It's that sort of number, which again, it is a lot of money without a doubt. But all of that money has come from this. There's no taxpayer money there. Don't panic if you're British and you're like, that's where my taxes are going. That's all come from private company investment and individuals investing in the project. And actually, if you put it into perspective, in the grand scheme of things, certainly in the context of motorsport, that's a drop in the ocean. If you compare that to the, the R&D budget of a Formula One team, you'd lose that down the back of the sofa. So you're considering what we're trying to achieve here. We've done it on a shoestring is the reality.
Absolutely. I want to find that sofa where that got lost, by the way. Got a question from Timothy. Are you worried about some other project breaking the speed record before Bloodhound?
Yeah, good question. No, I think, there are, I'm sure you're referring to some of the contenders. That there are probably the most realistic contender that's out there is a project called the Aussie Invader. They have set their sights on 1,000 miles per hour and are well down the road of building a car. There are some other land speed record projects out there in various states of development / disrepair. I think it would be exciting if there was another team out there who was a genuine contender. Obviously, I'd be gutted if someone else got there before us. And I do think, being pragmatic, if we get there in the next 12 months, 24 months, I think that will probably be the land speed record that lasts for the next couple of decades. I think the incentive to try, particularly if we got to the ultimate target speed of 1,000 miles per hour, which personally I think is unlikely now, given where we're at. But if we were to ever do that, I'm not sure a car will ever go faster than that.
Great. Yeah, and I hope you're able to bring it home first. No question about that. We're starting to run out of time here, so just a couple of last ones here. Does Bloodhound have a pressurized cockpit?
No, it doesn't. So, in fact, one of the things we discovered during the high-speed testing in South Africa at that time of year, it gets very, very hot. There's no aircon, there's no pressurization. Andy is breathing oxygen through a mask, but he basically just deals with the conditions in the cockpit, which get pretty extreme just because of the temperatures out there.
Excellent. Excellent. There are a lot more interesting questions here, but I see we're at 7 o'clock, so I think we better wrap up here. Ben, I think you were kind enough to offer some additional answers for people that were particularly interested in technical matters, or perhaps
Absolutely.
even
Please get in touch.
Yeah, please do. And we'll thank Ben once again. Thank you very much. A great talk, Ben.
Thank you very much. Thank you for joining with us this evening.
Great project. And just to plug the alumni lecture series some more, there are going to be some interesting talks coming up. I think you'll see some of on the screen. Things like, come on, ref, towards empathy for rugby union match officials, all the way to the DNA damage and cancer, the science and the opportunities. So there are a lot of interesting things coming up. Please, thanks for coming tonight. And hopefully this was, you were as interested as I was and fascinated by all of this, and come back and learn about some cancer and DNA and rugby match officials. So again, thank you and good night.